This is a comparison of methods to find heat transfer rates on a space shuttle tile. In this presentation, we'll be going over what heat transfer is and its applications in spacecraft, specifically analyzing work that Utah State presented on heat transfer in a space shuttle tile, and using our knowledge of heat transfer to improve upon their work. So what is heat transfer? Heat transfer, represented as Q, is the movement of energy due to a temperature difference. There are three types of heat transfer, all of which are seen within spacecraft: conduction, convection, and radiation. Going off of heat transfer, thermal resistance is another heat property defined as a temperature difference by which an object resists heat flow. Thermal resistance can be related to an EE circuit, where temperature is voltage, heat flow is current, and thermal resistance is resistance. Similarly, thermal resistance is inversely related to heat transfer. We have a few sources of thermal resistance, from conduction, from an inner object, and from an outer object. There are a number of properties of space that bring about challenges for spacecraft. The huge difference in temperature between the cold experienced in the vacuum of space and the heat seen in reentry conditions, along with the storage of liquids on board a spacecraft, all bring about their own unique challenges. Heat transfer is a big factor in spacecraft design, most easily seen represented in TCS, or the thermal subsystem of the spacecraft. This subsystem directly deals with temperature control of spacecraft, factoring in the changes in direct and albedo sunlight, IR energy emitted from Earth, and the internal heat regulated from the spacecraft. Some physical representations of this subsystem include, but are not limited to, the radiators, the thermal blankets seen on spacecraft, spacecraft heaters, and pumped fluid loops. Some significant people that helped us solve some of the big questions of heat transfer include Robert Diesler, Cy Ostrach, and last but not least, Robert Siegel. These NASA bigs most definitely got theories and coefficients named after them before we could, as they fundamentally developed our knowledge of heat transfer. Diesler worked at NASA Glenn and had a lot of recognition in turbulent flow and heat transfer of fluids and pipes. Ostrach's research led to semiconductor production, and he also designed a few experiments that were flown on the space shuttle. Siegel is one of the authors of Thermal Radiation Heat Transfer textbook, with numerous contributions to the field of heat transfer. We didn't start off with heat transfer being represented as these complex theories and major systems like we see in TCS, but humans have always needed to regulate heat. Basic examples of this include clothing and fires. Unlike spacecraft, however, we have the luxury of being protected from radiation via Earth's atmosphere. Once we reach orbit, we have to approach heat transfer in a little bit of a different way, as we're more impacted by radiation, which is more effective in a vacuum such as space. So imagine this: you're a tile on the space shuttle and you're re-entering Earth's atmosphere. You're going speeds of around Mach 25, and you're facing extreme temperatures around 1650 degrees Celsius. That's hot.
To analyze the heat transfer for a shuttle tile, some parameters need to be set. The material for the shuttle tiles analyzed in this study was Li900, and the density, specific heat, thermal conductivity, and temperatures listed on screen were extracted from the Utah State University that we will compare ours to. The composition of the tile is 10% silica and 90% air, with a borosilicate coating that absorbs 95% of heat. Here is a cross-section of an Li900 tile that shows dimensions. As you can see on screen, it roughly measures out to a square with 0.0232 square meters of area, with a thickness of 0.1 meters. The thickness can vary from 1 to 5 inches depending on where it's located on the shuttle, but for the purposes of this study, we will be using a thickness of 4 inches, which converts to 0.1 meters. Taking a closer look at the materials that compose the tile, you can see the ratio of borosilicate coating to silica, where the coating is much thinner than the silica. The slide on screen shows the difference in that thickness, as well as the thermal conductivity for both materials. And here you can see how the heat transfers through the material, where it is first exposed to the borosilicate coating before reaching the silica. To simplify our calculations, some assumptions need to be made. Those assumptions are that this would be analyzed at steady state, the changes in heat transfer from corners and edges would be neglected, which means we're assuming the tile is of infinite area, the surface temperature is uniform, and the altitude used for analysis would be set at 100 kilometers. On screen, you can see the values of density, dynamic viscosity, and airspeed using the 1976 US Standard Atmosphere model at 100 kilometers. And here you can see a rendition of a shuttle during reentry with the colors on the belly of the shuttle representing different temperatures, which is why the uniform temperatures is an assumption that we use. Additionally, you can also see that the colors are affected by the edges of the shuttle, which is why we chose to neglect those effects in order to make our calculations simpler. The equation used by Utah State for convective heat transfer is as appears on screen. That convective heat transfer equation also includes the heat transfer rates for conduction and radiation. You can also see a diagram showing the radiation and conduction flux on a cross-section of the tile. Using the temperatures and the tile thickness as shown on the slide, along with an emissivity of 0.85 for a gray body, the radiation from the surface and the conduction into the tile can be computed. With that, the rate of heat transfer due to convection can also be found as seen on screen. Looking at the radiation and conduction over the entire area of a single tile, the equations to calculate radiation and conduction from the previous slide are used again, but both are multiplied by the area of a single tile. The values of that calculation are on screen. This finishes Utah State's study, and now we will be moving on to our calculations. We first begin with the electrical engineering analogy that compares heat transfer to Ohm's law, which we have seen in class. This allows us to find the individual resistance for each heat transfer case, namely conduction, convection, and radiation. Starting with conduction, the calculation of the conductive resistance for both the silica and borosilicate coating are on screen, along with all the values needed to perform that calculation. With the conductive resistance, we can now calculate the heat transfer due to conduction for the entire tile, combining the conductive resistances for both materials. That value can be seen on screen.
Next up, we're going to find our heat transfer rate for convection. But before we do that, we have to find our Reynolds number at reentry. This is the equation for Reynolds number, where rho is equal to density, v is equal to velocity, d is equal to length, and mu is equal to dynamic viscosity. The Reynolds number at reentry is 60.7, which is well below the threshold of 2300 for laminar flow. This means the laminar flow occurs at reentry. Now that we have our Reynolds number, we can find the heat transfer coefficient for convection, which is HCx star. To find the local heat transfer coefficient, we need the Reynolds number, the Prandtl number, Cp, which is the specific heat, rho, which is density, and V infinity, which is the free stream velocity. Once you have your local heat transfer coefficient, now you can find your average heat transfer coefficient for convection using the equation below. Note that the Prandtl number uses mu, which is dynamic viscosity, Cp, which is specific heat, and K, which is thermal conductivity. Now that you have your average heat transfer coefficient for convection, you can find your resistance for convection, which uses this equation here, where Hc bar is equal to your average heat transfer coefficient for convection, and A is equal to your area. You can also calculate your heat transfer rate for convection, which is Qc. And to find that, you need your average heat transfer coefficient, which is Hc bar, A, which is your area, T tile, which is your temperature of tile, and T stir, which is the temperature of your surrounding. Note that our heat transfer rate for convection is negative, but that's good. We are expecting that because as we are taking in heat, we are expecting a negative convection rate because as you take out heat, that is a positive number, but this tile is getting hotter, so you are expecting that negative number. Lastly, we are going to find our radiation heat transfer rate. But before we do that, we have to find the heat transfer coefficient for radiation, which is HR bar. To find HR bar, we have to find the shape factor, which is F1 to 2. But since there's only one body and one surface, that means our shape factor is equal to 1. Epsilon is our emissivity, sigma is our Stefan Boltzmann constant, and T tile is the temperature of our tile. So now that you have your average heat transfer coefficient for radiation, you can find the resistance for radiation using this equation, where HR bar is equal to your average heat transfer coefficient for radiation, and A is equal to your area. You can also calculate your heat transfer rate for radiation, which is QR. And this equation uses HR bar, which is your heat transfer rate for radiation, the average one. A, which is area, T tile, which is temperature of the tile, and T star, which is temperature of the surroundings. And note here that your heat transfer rate for radiation is also a negative number, and we were expecting this. So as we conclude our presentation, we wanted to compare the two analyses. Note that Utah State did not have any analysis for your radiation resistance, conduction resistance, or convection resistance. On the other hand, Cal Poly went above and beyond to find those resistances on the right-hand column. In addition, Utah State did not have very complicated equations to find the radiation heat transfer rate, the conduction heat transfer rate, and the convection heat transfer rate. They used very simple equations that did not specifically tailor to that instance. On the other hand, Cal Poly did use specific equations to tailor to that specific instance. And you can see there's a difference in numbers. However, Cal Poly's analysis is much better because it's much more accurate because we use the specific equations. In summary, Utah State's analysis was no good, and Cal Poly's analysis was a lot better because we used the specific equations. Thank you for listening to our presentation, and now you know that Cal Poly's analysis is much better than Utah State's analysis. Thank you.